Alrighty, we are back at it. Let's do green. Green's such a great color for absolute value. So this symbol, these bars that you see right here, you've seen that again. We're still kind of just revisiting things from Algebra 1. These are absolute value. And that's exactly what it means, like the value. It really is asking you distance. And in this case, it's the distance from 0. So it's asking you what things have a distance from 0 of, in this case, 3. So if you think about that, here's 0. What's 3 units this way? 3. What's 3 units this way? -3. So both of those things have a distance of 3 from 0. So the direction doesn't really matter, and therefore both positive and negative. And I think students usually think, oh, absolute value is always positive. True. The reason is you're saying how far is it? So whether it's 3 to the right or 3 to the left, it's 3 units away. Now when you're solving the equation, you have to keep that in mind. I always tell my students that 2 bars, like you see for that, means 2 answers. 2 bars is 2 answers. So don't just ignore those bars when you see them on a test, quiz, homework, or anything. They have meaning. For example, here, up above, you could either have a +3 or a -3 inside those bars, and it would kick out as a 3, because you're saying how far is 3 away from 0? 3. How far is -3 away from 0? 3. So when you go to solve the equation, you have to keep in mind, like in this particular example right here, that you are going to have 2 options. In order for you to get a 7 out here, you can either have a positive or a -7 inside the bars. So you never change what's in the bars. X minus 5 and X minus 5. You never change that. But in one case, that would come out to be a 7, and in one case, it would come out to be a -7. So you're saying, hey, what's inside the bars can either be a positive or a -7, and that will give me the answer they're looking for. And then you simply solve each of those. So in this case, I would be adding 5, and I would end up here with -2. Or X could also have a value of, and when I add 5 over this side, it would be a 12. So you could either put a 12 or a -2 in there, and in the end, you would have 7 as your answer. So same thinking here. Ooh, not same thinking here. I'm just a little bit lost because my answer page does not look exactly like this. Okay, so in this problem, I have a problem. This is asking for the absolute value to be -4, but that can't happen. I can't do this because it's saying, hey, when is 3x plus 7 -4 units from 0? And you can't be negative. You can't have an absolute value that kicks out a negative. So you can't do this one, and you would say no solution. That's fun. Alrighty. Here, I have to get the absolute value part alone before I can split it and make my 2 equations. So I'm going to move this -10 over by adding, and then I'll have the absolute value of 3x plus 7 has to be 6. So now it's equal to a positive, and I'm good to go, but I'm thinking that means what's in the bars is either plus or minus 6 to kick out the 6. So what's in the bars is 3x plus 7, and that's going to either equal a -6, or 3x plus 7 is going to equal a +6. I never change what's inside the bars. The 3x plus 7 stays that way. The only thing I change is whether it equals the positive or negative version of my value. And then I'm just going to solve each one. So taking away 7 and dividing by 3. So one of my options is -13/3. There's not really a reason to turn that into a mixed number or a decimal or anything else. As you get higher in math, we just really leave them as fractions and improper fractions, so we just are going to leave it. I go over here and I solve the other option. And when I divide that by 3, I get that x could equal -1/3. So my options in the end are that I could have negative 1/3 or negative 13/3 and still end up with the proper answer. So here you have to be a little careful. Like here where you see the negative, it's straight up absolute values equal a negative, so you can't do it. Here there's a negative, but you have to get the absolute value bar alone first. So in getting rid of the negative 10, I added 10, which turned that into the positive number 6. So don't decide, oh, there's a negative somewhere in the problem, so therefore I can't do it. You really have to wait until you have just the absolute value bars on the left, and then see if the number it equals at that time is positive or negative. Let's carry on. Ooh, this is going to get tricky. The difference between less than and greater than. Thinking of absolute value as distance, here I would think of this as saying, okay, well, the distance from 0 is less than 4. You have to stay less than 4 units away. So if this is 0, 1, 2, 3, 4, 1, 2, 3, 4. You have to stay within this region between 4 and negative 4. Your distance has to be less than. I always kind of think of that absolute value less than 4, that's going to be like inside the fence. You have to stay inside the fence. You have to limit your distance. It also becomes an and problem or a between problem. You are in between the 4 and the negative 4 in this case. You just have to stay in between the two fence lines. So kind of keeping that in mind. Whereas if I have this, absolute value of x is greater, or I sometimes think of it as greater, because this is going to turn out to be an or situation. This is saying your distance is more than 4. So if this is 0 and here's my 4 and my negative 4, you're interested in the things that are out here, not the things that are in between, the things that are beyond that 4 and negative 4. So that's going to be an or problem. So when you set this up, you're going to have to do or problems. So this gets a little tricky because you have to look at the problem and say, okay, this is absolute value and this is an inequality. So I'm staying inside the fence. My distance has to be less than 4. So this has to be an and problem. And so I'm going to have my negative 2x minus 5, and it has to stay between the 4 and negative 4. And your little alligator mouths are always going to be opening to that same direction to the right. And now, just like we practiced on lesson 2, we have to go ahead and solve this. So you do have to be pretty confident about lesson 2 in order to do well on this, because it's using those same skills. And we're going to have to think about this next step also, because we're going to be divided by a negative 2. And when you divide by a negative 2, you need to flip everything over. So I end up with, on the left, a negative 1/2. I flip this over. My negative 2's cancel. I flip the next symbol over, and I end up with negative 9/2. So again, it does say to graph. So I have to think about this one a little bit. If this is 0, I'm just going to count these out. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm calling this negative 9/2 right here and negative 1/2 right there. And I am in between there. And it is not or equals. So I'm going to have open circle on each of those spots, both at negative 1/2 and at negative 9/2. And I'm going to be in between, because x is in between those two values. So again, whenever you flip, you got to kind of slow down a little bit and think about what you're doing, because the numbers end up in wonky spots. For example, here the negative 9/2 is on the right in this statement, but it's on the left in the graph paper. So you just have to kind of be conscious of that as you go. This is also greater, and so I would think a greater. So now this is going to be greater than or equal to. So I'm expecting little arrows that both go out, because it can be over here or over here. So we have to think, okay, your distance has to be greater than or equal to 7. So you're staying outside of the fence at 7 or negative 7. So my two equations, I never touch what's inside the bars, and then this equation is just going to be like it was. this arrow pointing this way will generate an arrow pointing that way. And it'll have an or equals to, so it's a dot. Then I go over here and I rewrite the equation again. Don't change what's in the bars, but I do have to flip this symbol over to make it a -7 here because I need arrows pointing both directions. So I want a less than here and a greater than there. So my symbols are also pointing out in two different directions. So for example, this symbol is pointing to the left, that arrow will go left. This symbol's pointing to the right, that arrow will go to the right. And then I just need to solve both of those. So I'm going to take away 3. And I actually would take away 3 here as well. And then I'm going to multiply by 2. So x is less than or equal to -20 is one of my options. Or here, if I multiply both sides by 2, I get x is greater than or equal to 8. So if I had to graph it, I'd say, okay, 8 is about here, and I need everything greater than or equal to that. -20 is, I don't know, way down here somewhere, and I need everything less than or equal to that. So I get my arrows, my ors that I was expecting from the start. So you really want to solidify in your brain like these kind of situations. What do I do if I have absolute value less than? I stay inside the fence, I get an in between. And what if my absolute value is greater than? Then I'm going to get an or statement where the distance is on the outside of the fence, so it's going outward. So do what you got to do to kind of learn that. This next thing is tolerance. Tolerance in math is kind of giving you like a little buffer zone, like a little bit of give and take. And so this is our formula, and you can see why we're studying it right now. M is going to be like the middle, your ideal value, the normal value, whatever they want to call it. T is your tolerance or allowance of error. So you're like, oh, you know, the average is 100, give or take 3. So it could go up to 103 or it could go down to 97 because I'm giving a buffer of 3 in either direction. And because it's going in either direction, that's how it ties into what we're doing right now. It's just about measuring that space. So this is just showing you if this is my middle mark, my normal, my expected number, my average, whatever your tolerance is, that's telling you how far you can go each way. Like think of it, what you tolerate, what you can do, what you can take. And then you're going to go up here and down here. So how far you end up, what that spread when it's all said and done is called your range of values. So this would be like the low end, and this would be the high end of that buffer. And then smack dab in the middle is that average value. So this is, if you look at this symbol, this is less than or equal to. And so you have to stay inside the fence. So that's going to be an and problem or a compound inequality that looks like this. It's going to be the between situation. So when we do tolerance, we're going to be looking at, like, they're going to tell us an average, and we're going to find the difference between some random number and the average or the mean. And then the difference between that number they give us and the average, it's the tolerance. So it has to stay underneath that tolerance. So let's look at it in action. The average U.S. woman is 64 inches tall. So that's going to be my middle number. Here's 64. With a tolerance of 5 inches. So they could be 5 inches taller, or they could be 5 inches shorter, just to be in the norm. So that's how that plays out. So if you kind of look through that, or think through that before you start, then you're going to be kind of less confused. So if this is the middle value, I go down 5, and then that could go down to like 59. And if you go up 5, that could go up to 69 inches tall. And so that's my range, with 64 being the middle. What it's asking me to do is write an absolute value equation. So that's what we were talking about right up here. We want to write one of these. So when you go to do that, you do leave an X in there saying, hey, whatever height that woman is, the difference between her height and the average, that tolerance has to stay less than or equal to 5. And it's, I mean, they have it in here as not having or equal to. It's not, you can't go outside of that tolerance. I'm not going to be really super picky about that. So in this last one, the horizontal bar used in gymnastics should be placed at 110.25. So that's going to be my middle ground, my normal number, whatever you want to call that. And it has a tolerance of 0.4. So you can go this direction, 0.4 by adding, or you can take away 0.4 and still be within the acceptable range. So if I did add 0.4 to the right end, I'm going to be at 110 inches, 0.65. And if I take it away, I'll be at 109.85 inches. So that's my range of values from here to here. That's the lowest you can set that bar at and the highest you can set that bar at. And then the tolerance is how far I went in either direction from that middle average number. So they want the absolute value inequality. Okay, well, I'm always going to have an X here saying some random number minus the correct, the average, the middle setting, which is 110.25, has to stay within the tolerance. And so you'd say that stays within 0.4. So you can go 0.4 in either direction and still be in the proper range. All right, that's a lot to digest. So rewatch any part you're having trouble with, and I hope that helps. Thanks, guys.